in our final unit of vectors, what we're going to do is we're going to be taking a look at a bunch of different objects. For example, lines. We're going to be looking at planes, like different in space and 3D. Okay. And we're going to see how they interact with each other, how we can get to the intersections between lines and planes and planes and all that stuff. Okay, we're finding basically, the applications of all this is solutions, right? Solving. Um, for these points of intersection or lines of intersections or whatever we have. Okay. But we're doing it with respect to the vector world. Okay. So what we're going to start with is, as we've got here, is the equation of lines in two space. All right. So we know from way back in grade 9, we had y equals mx plus b, right? The slope y-intercept form. We've had the slope point form, okay? And we've also had, sorry, that should be a y. We've also had standard form, ax plus by plus c equals 0, okay? Well, when we go from 2 dimensions to 3 dimensions, the first 2 lines, the equations, fail. They fail us. And the reason why they fail us is that the m represents the slope, and the slope is basically 2 dimensions. Okay? When we go to 3 dimension, we can't really talk about the slope in that same sense. So what we're going to have to do is recreate lines, okay, the equations of lines in terms of vectors. It's important to remember that we're talking about terms of vectors. Okay, the standard form, because it doesn't necessarily have the slope with it, okay, as one of its components here, it actually creates something else, okay, with our 2D and 3D. So we'll talk about that a little bit later. All right, we want to talk about how can we create, okay, vector equations. Okay, so we want vector equations of a line. All right, so here's what we're going to do. Okay, I've got our grid line here, and what we're going to do is we're going to take any line. All right, we'll just draw that here. That's any line there. Okay, and we'll just label this line. We'll say that we've got a specific point here. We'll call that point A that we know of. All right, and then any other point on this line is going to be considered point P. All right, so this P, we don't know what it is, but we know that it has an X and a Y, all right, coordinates to it. A, we're going to say, well, we know what A is. A is a specific point. That's A1, A2. It's on the line somewhere, okay, in 2 space. What we have to do is come up with an equation that will give us every single point that's on the line. That's what the equations do, all right? So what we have here, since we're dealing with vectors, what we want is we want a vector that is, in essence, parallel. It's in the same direction as our line itself, okay? What we call that, coincidentally enough, is our vector m, okay? Our vector m is not a slope vector. We don't call it that. We call it the direction vector. Okay, it's our direction vector. Why? Again, it's in the same direction as the line. Okay, kind of like you consider it as parallel with it. Okay, in the same direction. So how do we come up with an actual equation that gives us that point px? Well, here's some of the things that we need to understand now. That point A, all right, is the head of the position vector OA, okay? So we now have this as our, I'll just write it like this as a vector OA, right? We have P is going to be considered the head of our position vector OP, right? Actually, I don't like this, that capital letter A in there. It looks ugly to me. We'll just say OA, OP, we have that, all right? So here's what we have. OP, if we look at our addition, so I'm going to say using vector addition, we know that the vector OP is equal to the vector OA and the vector AP, right? From A to whatever point that is in whatever direction it's on that line somewhere, okay? We can see that. Now, AP is actually a scalar multiple of the direction vector, okay? AP is some scalar multiple of the direction vector. We know that. We set up, we've got the direction vector of M, right? Vector M, it's all basically parallel, right? It's in the same direction. So we've got this, so we can just exchange or substitute AP for TM, right? OA is the vector A1, A2. T is the scalar. Now M, the direction vector, we can just state that up above here as an M1, M2, right? So we've got M1, M2, the direction there itself, okay? OP, again, gives us our X and our Y, okay? So if we have a point that's on the line and the direction vector, we can come up with a vector equation. So this itself is the vector equation of a line in two space, all right, using the direction vector and a point, all right? Let's take a look at what that, what that means, okay, how we can do this or use it. Example 1. Determine the vector equation of the line passing through, we'll say the point -2, 4 with the direction vector let's say the direction vector is 3, 3, -1. Okay, so we have the direction vector of 3, -1. We have passing through the point -2, 4. All right, well, very quickly you can say, all right, well, our line, right? We always do vector equations, square brackets, is equal to the vector OA. The vector OA, square brackets, -2, 4, plus some scalar of the direction vector. Okay? That's it. That is the vector equation. All right? Now, how does that give us every point that's on the line? Okay? The key is this t, the parameter here. Okay? When we change the value of the scalar, we change the point. All right, for example, okay, if, oh, did the wrong one. If t is equal to 1, then we know that xy is equal to this vector equation, the addition equation, all right? And we can say that that is 1, 3, okay? That means the point, the point 1, 3 is on the line. We have that, right? You can quickly see if t is equal to 0, then we're back at the point negative 2, 4. So we have that as well, right? If we change the parameter again, let's say it's negative 2, then how do we find the other point? Again, negative 2, 4 plus negative 2 times 3 is negative 6. Negative 1 times negative 2 is 2. Add these together, you get negative 8 and 6. So yes, that's the vector, that's OP, right? So the point P that's on the line is negative 8, 6. Okay, remember you have to use the square brackets and the rounded brackets, right? One represents the vector, the other represents the point, okay? The vector, the position vector, right, is with the square brackets. The head of the vector we want, the point, right, is the one with the rounded brackets, okay? So that's how we're using the vector equation. Now, just like way back in grade 9 when we were trying to figure out different equations, we may not have the direction vector itself. We might just end up with 2 points that are on the line and we have to come up with the vector equation. Okay, so again, here we go. This is how we do it. Determine the vector equation of a line passing through, we'll say one point is 3, negative 2, and the other point is 7, 9. Okay. Well, how do we do this without a direction vector? We come up with the direction vector, right? We have to come up with the direction vector. The direction vector could be either AB or it could be BA. All right. So, because again, it just has to be in the same direction. The line goes in 2 different directions. So the same direction is one way and it's the other way, right? So it could be vector AB or vector BA. So in this case, what we have is 7 take away 3 is 4. 9 take away negative 2 is 11. Okay, so that's what we have. Since we have 2 points, one direction vector, we can use any point we want, right? Our vector equation could be 3, negative 2 plus scalar t and the direction vector, 4, 11. Okay? So there you have it. Remember, now the textbook does not use square brackets. They use rounded brackets. You must use square brackets. Whenever you give me your work, it is in square brackets if you're going to be talking about vectors. All right? We don't add points together, we add vectors together. And that's what this is. All right? Now there are 2 more types of vector equations or equations of a line, all right, that we're going to talk about here. And the first one is the parametric equations. All right. The parametric equations come from the vector equation. So if we start off with the vector equation, okay, a1, a2 plus t m1, m2, all right, what we do is we say, okay, well, the x and y vector is A1 plus TM1, A2 plus TM2, right? Adding those together, which implies that the X component is A1 plus TM1, the Y component A2 plus TM2. These are the parametric equations. Okay, parametric equations. All right. Now, we are going to use these later on as well. They're going to have a great use, especially when we start taking a look at intersecting lines and intersecting lines with planes and things like that. That's where we use these in particular, okay? So if we were to look at this last equation that we had, and I asked you to convert that into the parametric equations, all right? Pause the video, convert. What does X equal? What does Y equal? Remember that you are keeping it with the parameter T. So you should come up with X equaling 3 plus 4T, and Y is negative 2 plus 11T. All right. The X components must be equal to each other from one side of the equation to the other side, and similarly with the Y components. Okay, so that's what we can use. All right. Now, the third and final one is called the symmetric equations. Okay, the symmetric equations continue on from the parametric equations. All right, and since we have the exact same value or unknown as with T in each line, we are going to solve for the parameters. It tells us what the parameters actually are, okay? So for the X, we know that T is going to equal X minus A1 divided by M1, all right? And when we use the Y equation, this T parameter is equal to the A2, is equal to the Y minus A2. So we have Y minus A2 divided by M2. All right. Since the parameters are the same, then we just simply put these two equal to each other. And this is your symmetric equations. All right. This is the symmetric equation. And this is assuming that M1 and M2 do not equal 0. We'll have cases of those later on in 3D, which we'll talk about. Okay. But it's just playing with the numbers, doing some algebra, and going around, isolating for certain things. Okay. We have the vector equation, right? The vector equation gives us the symmetric or the parametric equation. And for the symmetric equation, you isolate. So you have x minus 3 divided by 4 is equal to y plus 2 divided by 11. Okay, that's what we have. All right, so we can figure out what the t value is in certain situations. If we know what the x is, we can come up with the y's and the t's and all the rest of that. Okay, so that's the idea. All right, you've gone through all of that. That's our first introduction then of this new unit. Good luck with these.